So this is the second video for chapter 15 on sound, and we're going to talk about the physics of music today. In general, there are three different devices that we're going to deal with and look at harmonics and resonance. One would be an open tube, open on both ends. Second would be a tube that's closed on one end, and the third would be strings. We're going to talk about the strings first, because this is something that we've done already back in the wave chapter. We had a question on several of the activities about the different the fundamental and then the second harmonic and third harmonics on a string. And this was a diagram that you actually saw in one of your review packets. So just look at that and understand that the fundamental frequency would be where the two nodes, the two ends are tied, and the only way we could do the simplest vibration would be to have one antinode in the middle. If we speed this up a little bit, you'll get two antinodes. You speed it up a little more, you get three antinodes, 4, 5, and 6. Those are the different harmonics for that string. Just a review about what nodes and antinodes are. A node is the part of the standing wave that doesn't move, and the antinode is the part that has the widest range of movement. On the string, you can see there we have one antinode on the first one, 2 on the second, 3 on the third. That would be the first, second, and third frequencies, harmonics. So for a closed pipe, which we haven't dealt with in sound, this would be something like a tube that has an opening on one end, and like a soda bottle when you blow across it. It's got an opening on one end only. The harmonics for this have a certain formula, and because the bottom is closed, you can't have even harmonics, because the first harmonic would be the sound coming out of the top. The second would be the bottom, but the bottom's closed. So you have to skip the even harmonics. So for a closed pipe resonator, something like a Coke bottle that you blow across and make a sound, the frequency, and we're going to say F sub n, frequency of the, in this case, let's say the first harmonic, is equal to n times the velocity of sound over 4 times the length. So in this case, n is 1, so it basically goes away because 1 is the identity number for multiplication. So we're going to solve for the fundamental harmonic, and that would be the velocity of sound over 4 times the length. So the 4 and the L are on the bottom. Once you solve for the first harmonic, you can't have a second, fourth, and sixth. So we have to solve for 3, 5, 7, and so on. Easiest way to do that is to take the first harmonic, multiply by 3. Take the fifth harmonic, or the first harmonic, multiply by 5, you got the fifth harmonic. So that would be how we solve for the harmonics on a closed tube. Remember, you need to know that a closed tube doesn't have even number harmonics, so the first harmonic is 1. The second one actually would be 3, but it'd be safer, I think, to say first, third, fifth, seventh harmonic. So that formula will be given, and you need to look over those formulas and make sure you know which one is for a string, which one's for a closed tube, which one's for an open tube. So that would be closed pipe. Here is a diagram of a closed pipe. You can see that when we say harmonic, it's all of the possibilities, not like the string, all the possibilities for vibration, but all the possibilities where the wave is expanding on the way out. And when the wave expands on the way out, you can hear it loudest. So if we put a tuning fork on the end there and let the sound go in, and it came out and it was expanding, it's like a megaphone. Seen a megaphone the cheerleaders have? You holler into the megaphone and the sound expands and it makes it louder. If you turned it around and talked into the big end, it would decrease the sound, and that would not be a harmonic. So what we're looking for on these harmonics, the first harmonic would be the first time that the wave is at an antinode at the opening. The third harmonic would be the first time that, or the second time that it's open at the end. And the fifth harmonic would be the third time that it's open at the end. So, and you can see the formulas here. 2, 4, and 6 don't happen because that end of the tube is closed. So next we'll talk about open tube resonators. And an open tube resonator would be something like a flute or something that has both ends open, and or even a tube that has both ends open and you hold a tuning fork next to it and the sound goes through. Here you can have the harmonics 1, 2, 3, 4, 5, 6. You can have all the numbers. For an open tube harmonic, again, the easiest way to do this is to take your formula at the very bottom of the page where it says Fn equals NV over 2L. Let's make N 1, and both of the N's basically go away because one's identity. So the first harmonic, first frequency harmonic, would be V over 2L. In other words, the speed of sound is V over the length of the tube times 2. That would be the first harmonic. How do we get the second harmonic? Multiply by 2. How do we get the third? Multiply by 3. So those are the harmonics on an open tube resonator. Here's a diagram of what an open tube resonator looks like, and looks like that's a clarinet because you can see the reed on one end. And again, on the open end, on both ends, notice that it's where the wave is at antinode. That is where we call the harmonic. So the first harmonic, second, third, you can see those harmonics in a picture of them on an open tube resonator. So on the resonance of a string, it uses the same formula as an open tube, and we've already talked about what first, second, third, fourth, fifth, sixth harmonic looks like, and you can have all the harmonics on a string. There's no skipping the even ones. Here's the diagram of the first, second, third, fourth, and fifth harmonics, and the formulas that go with that. So notice that on the first one, it's F1 equals V over 2L. We talked about that. On the second one, F2 is just V over L because the 2's cancel. So look over that. I will give you the formulas for the string, for the open resonator, and for the closed resonator. You need to know which is which. They're not going to be labeled. So you need to do a little bit of heads up and look over that. Sound quality. When we talk about sound quality, this in sound terms is a characteristic called timbre. It's spelled T-I-M-B-R-E, but it's pronounced timbre. And it's also called tone quality or color. The fundamental frequency is the lowest frequency at which the instrument will vibrate. We've looked at a string, closed tube, open tube. See all those possibilities. Whole number multiples of these are called harmonics. It's all kind of a review of the stuff we just talked about. Consonance and dissonance. Diss, you kind of think of when you diss somebody, you disrespect them. Think of dissonance as an unpleasant combination of tones. So if you put 2 or 3 or more harmonics together or tones together or pitches that made it sounded like something was broken, that would be dissonance. If you put, like on a piano, you hear somebody play different octaves of the same note, those go together well and they give you good sound quality or timbre, and that would be called consonance. It's a pleasant combination of pitches. For beats, when you have 2 tones that are exactly the same, you can't hear the difference between those. If 2 instruments played the same frequency and they were spot on, you wouldn't be able to hear the difference. But if one of the instruments was off by, say, 1 hertz and the other one was 1 hertz different, when you hear them, you're going to hear a beat, and it's going to be kind of an oscillation of sound, and the beat is equal to the number of beats per second. That's the difference between the twos. Subtract the big minus the small frequency, and that tells you what the number of beats are. So it's easy. Big minus small, the result would be how many beats. Now, if you have 50 or 100, you're not going to be able to discern that. But if it's somewhere between 0 and 10, you'll be able to hear that oscillation or that vibration. Interference, when 2 waves are combined, like if two people wiggled a rope on opposite ends and these waves came across and they hit each other, if you had a trough and a crest, it's kind of like a pile of dirt and a hole. When you combine them, you get level ground. If you had a trough and a trough, then it's going to be a deeper hole. If you have a crest and a crest together, it's going to be a deeper peak or a higher crest. So this shows destructive interference where opposites combine and you end up leveling out. And it also shows constructive where the same positives interact, and when you have those, they build on each other and add their energies. So just think of it like a number. If you have a negative and a positive, they cancel out. If you have two positives, they add together to give a bigger result. Constructive and destructive interference are the same way. You have possibly headphones that have noise canceling technology. This is what they do. They have a microphone on the outside that picks up the outside noise, and it synthesizes another wave that is the opposite. So it would be like the trough to cancel that crest, and it cancels that noise out from the outside so you don't hear it. So that finishes up day 2 of the notes. We'll have just a little bit more to add on, and we'll do that on the PowerPoint C and notes day 3. Work on your review some. You should have your PowerPoint B. Use the PowerPoint B and your book. You can answer most of the rest of the questions on your review. Good luck.
Could have been on TV, Mr. Anderson.
Do I need